So we are starting second part on the number theory, introduction number theory. Today we'll start talking about prime numbers. Okay. So the first part, if you remember, was mostly about modulo arithmetics, right? So doing operations mod n, and then now we start talking about prime numbers, and then you can expect that we will do many things mod a prime number. Okay. So prime numbers, by definition, these are numbers that have two divisors only. The number itself and one. They don't have any other divisors. They are very central to the number theory. So the number theory focuses a lot on usages of prime numbers and operations that involves prime numbers. One important thing is something called the fundamental theory of arithmetic. That's a theory that you have probably become aware of it since maybe grade 4, but not in this name, which says that any number, any integer number a, which is greater than 1, can be factored into a unique set of prime numbers and their associated exponents, right? So any integer number, a, can be factored into a certain prime number raised to a certain integer power, multiplied by another prime number raised to another integer power, and so on. How many of these and what are the powers and which prime numbers changes from one number to the other, okay? Generally speaking, here, we order them in an ascending way. So we assume in this representation that P1 is smaller than P2, P2 is smaller than P3, P3 is smaller than the next, and so on. Okay? This is known as the fundamental theory of arithmetic. And by the way, this theory has a proof, right? So it's not just something that it's an axiom or something. Okay? Anyways.
Isn't it like the statement itself is a proof?
Sorry? No, the statement is no statement which is a proof to itself. No such a thing. The statement is not a proof. The statement requires a proof. Is it true? Are you always going to be able to do this? And if you are always going to be able to do this, is it true for every number or not? Right? That's what the proof is looking for. Is this statement true? It means you can do it for every number and you can always find factors. Those two things are shown in the proof itself. And are the factors always prime numbers or something else? There are things that might sound intuitive to you, right? But mathematically, people of mathematics, they don't accept intuition. We need logical derivation that shows based on only basic axioms of math, which are very few, assumptions, right? Sorry?
Something said in the beginning.
Yeah, whereas not here. The axioms that you use for this is the fact that there is a prime number, right? That's an axiom. So we know that there are numbers, right? It's an axiom of mathematics. There are numbers that can only be divided by themselves or one, right? So that's an axiom of mathematics. There are several other axioms depending on which branch of math you are talking about. But anything else other than those axioms, in order to say that it's true and true for generalized cases, you have to provide a proof. So even this simple thing that any number can be factored into primes, and those primes, so you don't need anything non-prime in the factors, and the powers of the primes are just integers, proving that, and that it exists for every single number, requires some mathematical derivation, okay? So yeah, it looks very intuitive, but it requires a proof, and it has a proof, okay? So again, that like list of multiplications of prime numbers with certain exponents can be represented also in the compact form that you see up there, where capital P here is the set of prime numbers, and those APs, the exponents of the different primes, are integers and positive, so they are greater than or equal to 0. Okay, they are non-negative numbers. Okay, that's just the fundamental theorem of arithmetic. Based on that, you're doing your analysis of, so you can analyze any number to its prime factors, and you use that analysis to find the greatest common divisor and the least common multiple, and all these things that you have been doing in early arithmetics of K to 12 math. Okay, here is a table that shows you the prime numbers up to 2000. Again, currently there is a very big list of prime numbers to a very large scale, and there is a prize if you can find a new prime number, by the way, and it's not a small amount of money. But in order to do that, you actually need to write very complicated computer programs, and you might keep running them for a long time. But if you find a new prime number, you can get actually a nice recognition and prize and everything. Okay, I think it's in tens of thousands.
Okay.
Yeah.
Also, those prime numbers used to security also in ATM card and
Yes, they are used for many applications. So particularly when we talk about that, that's why we study this part actually, the number theory.
Computers can find them easily, right?
No, not easily at all. It's very difficult. We will see also a couple of algorithms, but all of them are complicated, especially when you go for larger values. There is no defined formula. The only way is to keep searching and testing. But if you can do a little bit more clever search, a little bit more clever test, that's the only thing that you can do. But there is no generalized formula that allows you to just generate prime numbers. Yes?
Even quantum computer.
I don't think there is some efficient algorithm in quantum computing that can easily find prime numbers. It can do factorization, but easily finding prime numbers, I believe I haven't seen something like that. I don't know. Okay. One important theorem, we'll come to it later because it's going to be useful for building up some other important stuff, is the Fermat's theorem. He has, by the way, Fermat has many theorems in the domain of number theory. This one is called Fermat's little theorem. So that's the small theorem of Fermat. There was one that was outstanding for a very long time in terms of proof. It was called Fermat's last theorem. That was the last theorem he came with before he passed away. And he did not provide a full proof for that one. So it stayed actually outstanding for a proof, I think until 10 years ago or less than 10 years ago. And the proof of that came out in, I don't remember, 45 pages, something like that. Yeah. And it was one of the problems outstanding in the mathematics and well known, the Fermat's last theorem. Okay. But now we are not going to touch on that theorem here. So Fermat's little theorem says that if you have P, which is a prime, and A, which is any positive integer, but it's relatively prime to P, right? So A is not divisible by P. You cannot divide A by P, okay? Then you can write this equation and it's correct. A to the power P minus 1 is equal to 1, or actually congruent to 1, okay? Mod P, okay? Or if you multiply both sides by A, right? You can say that A to the power P, so these are two ways to write the same theorem, okay? A to the power P is equal to A mod P, okay? So this one or this one are two ways of writing the same theorem. So again, the conditions here are that A is a positive integer, P is a prime, and A and P, they are relatively prime. So P does not divide A, okay? If all of this is true, then you can write, it's always true that A to the power P minus 1 is going to be congruent to 1 mod P. Okay. Any questions? Okay. There's another important, yes? Was the last class that you missed. Okay. There's another important theorem also called Euler's theorem. We'll come to it. But before going to that theorem, we need to define a certain function called the Euler's tangent function. And the Euler tangent function is defined as we see it here is the number. So phi, the Euler tangent function of an integer n, is the number of positive integers that are less than n and they are all relatively prime to n. We know what's the meaning of two numbers being relatively prime to each other. There is no common divisor between them except one. Okay? So the Euler tangent function for any positive integer n is defined as a count how many numbers are there smaller than n that are relatively prime to n. Okay? Here we see a table of some values of that tangent function for different values of n. So for example, let's take one example and try to see whether the value that we see makes sense or not. Let's take the example of 14. Okay, so how many numbers are smaller than 14 and they are relatively prime to 14? So let's start. 1 is always the case because 1 has only a common divisor equal to 1 with anything else, right? 2 is not. 3 is. 4 is not because there is a common factor between them, which is 2, right? 5 is. 6 is not. 7 is not. 8 is not, right? Because 8 has a common divisor 2. 9 is relatively prime to 14. 10 is relatively prime to 14. No, it's not, because it's any even number is not going to be relatively prime, right? 11 is, right? 12 is not. 13 is. And then we stop there, right? Because it has to be smaller than. So we counted 6. Yes?
But why 10 is that one?
Because 10 has a common factor with 14. 2 at least, right?
So it's not. Ah, okay.
Okay. It's not.
No, I just misheard.
Okay. So, and you can easily figure out that for any prime number, what's going to be the value of phi of n?
Smaller than the number?
I'm a small, it's always smaller, but what's going to be the value?
Oh, every number less than it, because every number is.
Yeah, so what's going to be the value of phi of n? Phi of n, exactly. So phi, that's a general rule. Phi of n is equal to n minus 1 if n is prime.
Ah.
Yeah. Yes. Okay. So if n is a prime number, then the Euler tangent function for that prime number is just the number minus 1, because every other number smaller than a prime number does not have any common factor with that prime number, right? Cannot happen. Okay. That's otherwise it will violate the definition of prime. Any questions so far? Okay. So now that we have defined the phi of n, the Euler's theorem, which is kind of, you can think of it as an extended version of the Fermat's theorem. So Fermat's theorem was limited to A and P, where P is prime, right?
Yes.
Now we are talking about A and N, where N doesn't have to be a prime. N is any integer, but we don't use N, we use the tangent, the Euler tangent function of N as part of the theorem, okay? So the theorem, the Euler's theorem, says that if you have any positive number A, positive integer A, and positive integer N, under the condition that A and N are relatively prime, so we had the same condition there, that P, the prime number, does not divide A, right? Okay, here we say that A and N are relatively, so there is no common factor between them. Then we can say that A to the power phi of N is equal or congruent to 1 mod N. Okay? And again, you can multiply both sides by A, so it ends up being A to the power of phi N plus 1 is equal to or congruent to A mod N. Okay? So this is Euler's theorem. You can think of it as an extension of Fermat's theorem, but for any number n rather than for prime numbers only P. Okay?
And we don't use that number, we use its phi.
Yeah. So again, if you try to, I said that this is a more general form, right? If n is a prime, can you show me that this reduces to Fermat's theorem?
Because that would be n minus 1.
Exactly. So simply, if n is prime, right, then phi of n is equal to n minus 1, and then the theorem becomes a to the power n minus 1 is congruent to 1 mod n, which is exactly what we have seen before, but instead of n, we wrote it as p. And we said n is prime here, so it's the same thing, okay? So simply, Euler's theorem is just an extension of Fermat's theorem for any integer n. No questions? No questions. Life is good. Life is good. Now we go to the question about finding prime numbers. Okay. There are, sorry, not finding prime numbers. Testing for primality. So if you have a number and you want to figure out whether this number is prime or not, what's the most, you call it what, brute force way to do this?
Divide and then see if it divides or not.
Yeah, so you keep dividing over what?
Dividing the whole of the smaller number.
Yeah, over all the smaller numbers,
Yeah.
right? Okay. Is there a more clever way?
So the most brute way. Most clever.
So first thing is you probably need to do a quick check. If it's even, it's not prime. So you try. So this remove a good number of values from your right. And there are some other known criteria like numbers that divide by 3, numbers that divide by 5. Those are also easy to find, right? So you'll probably start by even, then you terminate. If it's odd, you need to continue, right? And now you have removed half of your search space. And then you go for odd numbers. You see if for some reason they divide by 5. So the last digit is 5. Because the last digit is 0, does not work. Last digit is 0 is even, so it's already excluded, right? So you just check the last digit. And the sum of the digits, if it's divisible by 3, then the number is divisible by 3. So now, if it doesn't fit any of those, then you go for the next stage, which is probably searching for divisors, right? And typically, divisors of a number, right, will not be very close to the number. They are typically at least 1/2 away from it. So you start searching, so you move, if the number is odd, the 1/2 is gonna be half plus half. So it's gonna be one step after half the number of counts, right?
Okay.
Why do you say typically? Why is this not always?
It's always, not typically, okay? Yeah, you are right. So the correct statement is a divisor is gonna be less than half that number, right? So you start searching only less than half the number, okay? And you start going down until you find some divisors. That's brute force. All of this is still brute force, right? Now, there are more like smarter ways. Until very recently, there was no deterministic way to test for primality. The best known and efficient way was called the Miller-Rabin algorithm. This is a randomized way, so it's not guaranteed to reach the solution. It just, sorry?
Is it a numerical method, basically?
It is a numerical method, and as I mentioned, it's a probabilistic method. So the search itself is done in a probabilistic way, and it can negate, so it can tell you that this number is not prime, but in some other cases, it can say what do you say? What? What's the word? You cannot determine. What they call it? Undetermined, but it has another wording. So either you will get not a prime, or you will get out of it that it's not determined. And then in that case, you probably need to do further investigations to figure out whether it's a prime or not. Okay? And this is called the Miller-Rabin algorithm. Sometimes they call it Rabin-Miller, Miller-Rabin. Doesn't matter which one gets his name first. And the idea here is, here are some properties that allows this algorithm to be developed, okay? Some of those properties is that any positive odd integer, so again, we said we care about the positive ones, right? Which is greater than or equal to 3, so starting from 3. That odd integer can be expressed as, if you subtract 1 from it, it will become an even. And then this means that it's going to be represented as 2 to the power of some integer k multiplied by some q which is not even, right? So any odd number, if you take n minus 1, this will become an even number, and that n minus 1, which is an even number, can be represented as the multiplication of some odd value, q, multiplied by 2 to the power k, which is all the even factors taken out, right? All the powers of 2 taken out, okay? If p is a prime number, right, that these are some other properties as well. If p is a prime number and a is some number greater than 0 less than p, then a square mod p is equal to 1 under one of two conditions, and that's if and only if, okay? And I want you to tell me why, not with proof, but just with logic, okay? So if p is a prime number and a is some number which is less than p, smaller than that prime number, then if you take the square of that a, right, and you calculate that mod p, the prime number, the result is going to be 1 only in one of two cases, okay? If a mod p is equal to 1, or if a mod p is equal to p minus 1.
P minus 1?
Yeah. Okay. Why this is the case? At least testing it from the other way. If a mod p is equal to 1, then again, right? 1 squared will give you the same thing. So in that case, a squared, right? So if it's a mod p is equal to 1, then a squared mod p is definitely equal to 1, right? Because it's just a times a, right? And we know that any operations mod p, if you multiply two numbers mod p and each one of them is equal to 1 mod p, then the multiplication is going to be also equal to 1 mod p, okay? The other option is if a mod p is equal to p minus 1. Well, it's explained here, right? For a mod p to be equal to p minus 1, this means that a mod p can be also be written as minus 1 mod p.
That means A is negative.
No, the a is not negative.
Did you replace A with minus 1 or what happened?
No, I'm just saying that I can think of this. I can think of a mod p equals p minus 1 as a mod p is equal to minus 1
Okay.
mod p.
Sure.
Okay? Why?
A equals minus 1.
What is mod if we say a mod p?
Yeah, we said we can
It's
get,
the remainder, right, of a over p.
we said we can get negative remainders, but we only chose to consider the positive. Right?
Yes, exactly. So now let's look at whether those two things are equal to each other or not, right? And if they are equal to each other, why does it fit as another property, okay? So the remainder of a divided by p is what remains after you do the division, so, right? Okay. Now, if a is equal to p minus 1, that's the case that we are looking at, right? What's the remainder of dividing p minus 1 over p? There are two ways to look at this. Either you say that the quotient is 0, so this is equal to 0 times p, and then the remainder is p minus 1, right? Or you say that the quotient is 1, 1 times p is p, and the remainder in this case is minus 1, right? So those two things are equivalent to each other. It's only that we chose only to use the positive side in our general representation, right? So now we agree that those two things are the same.
Yes.
Okay. Now, if those two things are the same, why does this condition that a is equal to p minus 1 still fits that a square mod p is equal to 1? Because minus 1 squared is 1, right? So if a mod p is equal to minus 1, then a square mod p is equal to 1.
It's just the division at the
Yes, and then this means that if a is equal to p minus 1, then a squared mod p is equal also to 1. Okay? Clear? Okay.
somewhat.
So ايه اللي مش clear فيه؟
Yeah, it's clear, but يعني
It's wrapped around, yeah, wrapped around, but I think it's clear, okay? So that's the second property that we need to keep in mind for this algorithm. Okay, so we talked about number one, that any odd number can be represented using this representation. And then the second thing is that the property that if P is prime and A is smaller than B, then A square mod P is equal to 1, if and only if those two conditions happen. Again, we did not go into why it does not happen for if it's not one of those two conditions, because if and only if means it doesn't occur for any other values, right? That requires a proof, but we're not going through any proofs here, okay? Now the third one is if P is greater than 2, which is a prime number, and A is greater than 1, less than 1 minus P, 1P minus 1, we can write, of course, right, P minus 1 equals 2 to the power K multiplied by some Q, right?
Okay.
That's correct. Then one of the following conditions is true. A to the power Q is equal or congruent to 1 mod P, okay? Or there exists a J greater than 1 less than K such that this thing is true. Any number, any integer between 1 and value K.
Doctor, just a general question, what are these used for, and just to get the verbs behind it?
Those conditions are the key elements that enables the algorithm that we will see in the next slide to be developed,
To define whether it's a prime or not?
to test for primality.
Okay.
So these conditions are things, or these properties, are things that allows us a little bit to understand how the algorithm that we'll see in the next slide works, okay?
Because we got lost somewhere when you left.
The last one?
Yeah, the last condition.
Okay, so let's look it up clearly. Let's remove scratches because,
Can you start from the beginning of the second property? Yeah.
yes, that's what I'm trying to go through. So, you mean this one, this
P
property?
greater than 2 is prime.
Hmm?
No, I'm talking from the beginning of the second property.
Here?
Two main properties. If I mean the second
The beginning of the second, no, this one.
There is 3, not 2. But he's talking about the beginning of the third one, yeah.
Here?
No,
Which one is the second property? This one or this one?
This is the second property.
Okay, so I was pointing here and you were not saying yes. Ah, you couldn't see it, really? I was, okay, sorry. Okay, so it says if you have a prime number which is greater than 2 and some integer A which is greater than 1 less than the prime number minus 1, okay?
less than mod that number, يعني?
مفيش مود أي حاجة هنا. A is less than this number P, right? Minus 1, okay? If we note that we can write P minus 1, so note that since P is a prime number, it's an odd number, and since it is an odd number, I can write it in the format that P minus 1 is equal to 2 to the power K multiplied by some Q, okay? Then one of the following conditions, now we are talking about an A which is smaller than P minus 1, okay? One of the following conditions is true, either this or this, okay? A to the power Q is equal to 1 mod P, or congruent to 1 mod P, and then the other is there exists a J greater than 1 less than K such that A to the power 2J minus 1, okay, 2 to the power J minus 1 multiplied by Q is congruent to minus 1 mod P.
Where is K? Where is K?
K is here,
Okay.
Q is here,
Okay.
right? So I wrote P minus 1 already as this format.
Okay.
Now, after doing this and considering that A is greater than 1 less than P minus 1, okay, then either A to the power Q is congruent to 1 mod P,
Which is
or I can find some J which cannot be greater than K and not smaller than 1, okay, some integer value, such that A to the power, A that is that integer, to the power 2 to the power J minus 1 multiplied by the Q that we have here, okay, is congruent to minus 1 mod P.
Okay, so it's either it's one of the two, صح؟ يعني
Yeah,
it's
one
either
of the
this
two
or that.
conditions is true.
طب دكتور what is this property proving exactly? Because
It's not proving anything. It just says that this is a case.
Okay.
This is something to keep it in mind. Okay?
The only difference, let's say, in the output is one mod P and
There
minus
is,
one mod P.
this did not prove anything. This did not prove anything. This did not prove anything. This is just a property that exists.
Okay.
Tamam? Okay?
Why is it J minus 1 not just J? Yani you're saying that J is any number between 1 and... Oh, so
Because
the
you-
number has to be less than 2 minus K minus 2, I guess.
Sorry?
Why is it J minus 1? That's easy.
Why we have j minus 1 here?
Yeah.
Is that what you are saying? I think the only reason is we don't want to reach k.
K minus 1.
It has to be less than k somewhere.
Oh, okay.
So we don't want to reach k.
Okay, so it could be just 1...
Otherwise, we could have looked for another number j that does not reach k probably. Okay?
Yeah.
And then it would be just 2 to the power j.
Okay, so they could have done like 1 less than J less than K minus 1 and it would have done the same thing.
Yeah. It would have been 0 and up to k minus 1.
Yeah.
Yeah. And then you use that number,
This
call it
makes
I
sense.
or whatever. Okay?
Just a notation,
I think it's only to avoid going to the power 0. Yeah.
Yeah.
So just again, these are properties. It says that if this is the case, then one of those two conditions is true.
But in other case, how did the guy found out this and since it's property? Yeah. Was he just sitting and said, okay, if this is...
I think I didn't really look up the justification for this, but I think it's gonna rely to some extent on the Fermat's theorem and the so it's gonna rely on the Fermat's theorem and the other one, the
Euler?
Euler's theorem. Yeah.
Yeah, isn't 1 would be is equals to B?
Here? La, 1 mod p is not equal to p. Why?
Either 0 or
Who? What?
either 1 would be equals 0 or P.
Where does this come from?
I think he's talking about the mod operation, not 1 in mod P. And he's saying 1 mod with P.
1
Mod P.
Mod operation. Yani not,
mod
not the,
p
the mod
is
is
equal to 1, and I don't know what you are talking about. Why this is equal to 0 or p?
The remainder of
Remainder of dividing 1 by p. What's the remainder of dividing 1 by p?
is P.
No. You divide 1 by a value p. The remainder is going to be p? No. The remainder is something smaller than the number that you divide by. So it's something smaller than p, right? And it has to be somewhere between 1 and p. If you divide 1 over p, what's going to be the result of the division?
The quotient is 0.
That's the quotient. And what's the remainder? 1. Right? So where did this 0 or p come from? You got it? Well, لسه confused about it. Okay, so it's not the quotient. It's if we want to represent 1 as a function of p, then this is equal to some quotient multiplied by p plus some remainder. For the case of 1, this is going to be definitely the quotient is 0, because again, we say that p here is some number greater than 0, right? So it's going to be 0, and the remainder, it has to be 1. There is no other option as well, right? So 1. Except if p is equal to 1. That's the only case where this is not going to produce 1. Okay? خلاص? Any other questions? Well, this one is interesting. So minus 1 mod p is what?
P minus 1.
Exactly. This is p minus 1.
Using the previous one.
Yeah, well, just not the previous property, just using the definition of
Okay.
a minus mod some value, right? Okay. So now based on that, the Miller-Rabin algorithm works as follows. Okay. If you have a value n that you want to test for its primality, then you find some integers k and q, where k is greater than 0 and q is odd, so that you end up with this. Remember? The first representation, right? And then you select some random integer a, which is greater than 1, less than n minus 1. Okay. And you start testing as follows. Yeah, it says inconclusive. Sorry, that's the word that I was looking for. So you start testing as follows.
Like Coven.
Hmm?
Like Coven.
Yeah, inconclusive like COVID, exactly. Like the COVID test that we suffered from. If a to the power q mod n is equal to 1, then we don't know. It might be a prime number. Okay? And then the other test is for j equals 0 up to k minus 1, so this relies on the second property. This relies on the first property. Tamam? For j equals 0 up to k minus 1, if we can find that a to the power 2j q mod n is equal to n minus 1, then in this case we say, again, inconclusive. It might be a prime number. Otherwise, if those two conditions do not satisfy, then we are sure that the number is a composite number. It's not a prime number. Okay?
But doctor, I didn't get the condition in there.
Yeah. Here? ايه اللي you didn't get?
It's the second property that we.
Wasn't it j minus 1?
Yeah, now they change the convention again.
Yes.
So this is big J and that one is small j?
لا لا يا ما فيش big J و small J.
Then this one from 0 to k minus 1, صح?
Yes.
Yes.
Exactly.
Yeah. Okay.
So I'll just use big J and small j.
Okay. And equals n minus 1 here is similar to saying equals minus 1 and when we saw it in that property.
Yeah.
Right? Okay. So again, the number goes as the algorithm goes as follows. If you get a prime number, then you factor it out to this using this representation. So you take that, sorry, if you get a number, then again, if it's even, you just reject it from the beginning. If it's odd, then you start executing this algorithm. Take n minus 1 and get all the factors of 2 out of it. So now you figure out what's k, and you can also figure out what's q. So keep dividing it by 2 until it's no longer divisible by 2. Then you see how many times it was divisible by 2. This will give you the k, and the remaining number is going to be your q. Okay? That's going to be an odd number as well. Then you start selecting any random a, which is greater than 1, less than n minus 1. Now, this selection of a random value a, which is greater than 1, less than n minus 1, is the reason why we call this a randomized algorithm. Okay? And also, we call it a non-deterministic or a randomized because we are not conclusive all the time. Sometimes we can make a decision, sometimes we don't know. Okay? Then you start. You already figured out q. Now take that random a that you selected, raise it to the power q, and then calculate this mod n. Okay? If this is equal to 1, then you know that it's not composite, but you don't know. Or sorry, you don't know. You don't know. It's not composite.
You know that you don't know.
You know that you don't know. You are inconclusive. You don't know anything. Okay? On the yeah, Schrodinger's cat. On the other side, you go for another test, right? Now, if this test doesn't go through, so you don't finish here, right? Okay, so if this test just takes you to true, then you stop here and you say inconclusive. Now, the other test is for j equals 0 to k minus 1, you perform the following. You take the value a, the random value a, you raise it to the power 2j q, and you calculate that mod n. If you find it equal to m minus 1 or to minus 1, whichever, okay, then you say again, I don't know. Otherwise, this does not happen, this does not happen, then you say, I'm sure this is not a prime number.
So that's for, let's say, step 3 and 5. If it's equal to anything other than 1 or minus 1, then that number is not prime, right?
Is not prime.
Okay.
Immediately takes you to composite number. Okay.
So in these two steps, it's either prime, it's either inconclusive
Or non-prime.
Okay.
Okay.
But when do you reach the step to say, okay, this is prime?
Never.
Never?
You will have to do extra test. So if your number ends up in one of those two, the inconclusive situations, you have to figure out another way to actually confirm if it's a prime number or not. The algorithm actually shows that with very high probability, and there is a particular expression for that probability, the number is going to be prime.
Okay.
But there are certain cases where it's not a prime number. Okay? That's why it's inconclusive.
And the output is either not prime or we don't know.
Yes, exactly. Or you need to test further.
Okay.
Yeah. Don't know means you need to test one, like do something else.
Go and
Yeah.
investigate.
Yeah.
this is not a good sifting method, because then you're sweeping through a bunch of different random A's, and for each one you're going from
No, you don't have to switch across random A's. You just select one.
Yeah, but if you got inconclusive for you will have to try multiple A's.
So maybe you can try another A that will make your decision more conclusive. But then again, even if you swipe through all the A's and all of them tells you that you are still inconclusive, so probably you need to try something else, right?
Yeah.
Again, the idea is it has been analyzed, and this is mentioned in your book, right? It has been analyzed, and it was found that like more than a very high percentage, like I think it's above 90 something, okay, of the inconclusive cases are actually prime numbers, okay? Very few cases of the inconclusive are non-prime numbers, okay? So that's why they use the algorithm, and they just hope that what they get out of it is a prime number. The nice thing about it is it's very quick, right? Because you don't need to search. There's almost no search here.
Not
Right?
prime, or we don't know.
Yeah, but it's a very quick algorithm. That's why it's, by the way, it's still used until today to discover prime numbers, okay? Or to test for primality,
The
okay?
operation of sweeping of different J's from 0 to k minus 1.
That's again not a very big,
Okay.
operation,
Oh,
right?
because k is the exponent of 2.
Exactly, which is not going to be a very big number
Yeah.
anyways. Yeah.
It's a limited number of divisions
Yeah.
or whatever.
When you to the power of something, not really.
Okay. Yeah, so basically there is a paper by those guys which was developed in 2002, right? And that one actually has a deterministic algorithm to test for primality. So it's, if you go through that, you reach conclusive decisions every time, whether a number is prime or not. But the complexity of that, the number of calculations that you have to do are much, much larger than the Miller-Rabin algorithm. And that's why until today, people prefer to use the Miller-Rabin algorithm, okay?
Even with the GPUs and
Yeah, even with GPUs, but you need to consume a lot of the GPU calculation time to test for primality. It's probably easier to go for something, even if it's not successful every time, but successful most of the time, then it will save you a lot. Because the analysis here will be an average analysis, how many times you miss, right? Versus how many calculations you need to do.
When we're talking efficiency here, we're talking time.
Efficiency can be calculated in terms of time, but time is not a standardized measure. Typically, they do this in number of operations that you have to do. Because the faster your computer is, the less time, but still you need, if you want to compare with one measure, for fixed computer, or what we say is the number of operations. And then faster computers will do those operations in shorter time, but still it's still a number of operations, right? Last thing that we will discuss today are two topics: the Chinese remainder theorem, which is a very important theorem, and something called the لا مش Japanese, no, مفيش Japanese. In this part مفيش Japanese. There are probably some Japanese theorems, but we are not going to touch upon them, okay? And the other thing is the discrete logarithm, okay? So discrete logarithm, I prefer to leave it for next time. It requires a bit of details behind it until you understand the concept, not easy to grasp. A Chinese remainder theorem, we will just discuss the general description of the theorem. What does it say? What does it represent? But again, I will leave applications and calculations of that to next time, inshallah. Okay, so we do that next lecture. This theorem originates in 100 AD, so قبل الميلاد. Okay, it's a very old theorem.
After.
AD after, sorry, 100 miladi. Okay, BC 10. Yeah. Okay, and the it's not 100% sure, but it's believed that this mathematician Sun Chu is the one who came up with this theorem. Yeah, this is how he looks, right? Okay. I like that comment. It's nice. Yeah. It's actually one of the most useful results. It allows us to analyze a number in factors, but those factors do not have to be prime factors. but they are relatively prime to each other. That's the essence of the Chinese remainder theorem. And not only that, once you do that analysis, any operation between any two numbers, you can actually do them based on the analysis itself, not the original number representation. So let me a little bit elaborate on what I mean by this before we go into the description of the theorem itself. Okay. So imagine that I was able to represent a number, x, right, in terms of some coefficients, a, b, and c, multiplied by some factors. Okay, let's say m1, m2, and m3. Okay, where those factors m1, m2, and m3 are factors of the domain or the modulus that I'm dealing with. So now we are talking about x mod some m. Okay, and then I take the m, break it into components. I call those components m1, m2, m3, such that those components, you can think of them as in vector space, they are orthogonal to each other. Here in number space and in number theory space, we say that they are relatively prime. There is no common divisor between them, of course, except one. I don't have to repeat that except one every time, okay? And then I can represent my number x mod m1 with a factor a, mod m2 with a factor b, and mod m3 with a factor c, or basically x mod m1 is equal to a, x mod m2 is equal to b, x mod m3 is equal to c. So these, as if I'm analyzing my number x in the directions of m1, m2, and m3, right? Again, just trying to think of it as a vector representation. In numbers, we call this, if it's, for example, k, the number of these is k, we call this a k tuple. Okay? So now I was able to represent my original number x, which was actually mod some original space m, tamam? After I analyze my space into different components, I call them m1, m2, m3. I can represent x as a component in the direction of m1, which is simply x mod m1. And as a component in m2, x mod m2. As a component in m3, x mod m3. Okay? The results of that, in this case, for example, that's a 3 tuple, right? And I will have the values a, b, and c as the 3 tuple. A is equal to x mod m1, b is equal to x mod m2, c is equal to x mod m3. Okay? Now, once I did this representation for the number x, and maybe I do the same for the number y, I can simply later on, if I want to do x plus y mod m, okay, I can simply do a, b, and c. Let's say these are the components of x. And I have another analysis for y, right? by and cy. If I want to add them, I can simply add those components, similar to what we do in vector additions, right? We add the x's together, we add the y together, we add the z together. And the result that I will get from that is going to be simply the result of the addition, right? Mod m, the original space, okay? And I can always take it back from the subspaces to the original space. Yes?
Is there an assumption here between the relation of x and y?
No. X and y are any two numbers, but I'm representing them in m1, m2, m3, where the assumption is that m1, m2, and m3 are the factors of m, the main modulus, and they are relatively prime to each other.
Okay.
So these are the conditions, that m1, m2, and m3, number one, multiplying them together gives you m. So this is factors of m. Number two, each one of them is prime, relatively prime to the other. So there are no common factors between them, but they are not prime. They don't have to be prime numbers. Okay? Now, if I've done this and I was able to get x mod m1, x mod m2, x mod m3, which is what I call ax, bx, y, cx, and I was able to get y mod m1, y mod m2, y mod m3, which I call ay, by, cy. If I want to add x and y, I can simply add their representation in the subspaces m1, m2, m3, and so on, right? And if I want to multiply, I can multiply the components. I want to subtract, I can subtract the components, right? So rather than working with the original big number, m1 and m2, I can work actually with much smaller numbers, which are the components of those in the spaces of the relatively prime numbers.
Is that why they use GPUs?
Here is not that much relevant to GPUs. This is kind of reduction of calculation. So this is probably before the GPU era, where people were doing things by hand or with slow calculators. So they wanted to reduce the amount of calculations that you need to do when you are dealing with very large number by breaking them into smaller components with sub M1, M2, M3 are smaller modulus, right? So now you can deal with that in a smaller space. Okay? And of course, if you want to make the components smaller, you increase the factors, right? So rather than breaking it into only 3 components, you can break it into 10 components. Each one of them is a piece of the original number, right?
2 questions.
Yes.
The first one, A, B, and C can be 0, صح?
Yes.
Okay. The second one, does a k-table exist for any number, given that you don't have a limitation on k, as long as it's smaller than...
لا, of course no, because you cannot break any limitation on k.
Or prime numbers.
Yeah, again, limitation on k, the size of or the dimension of that representation is going to be how many relatively prime components you can find for your space M,
Yeah.
for the modulus M.
But my point is, if you have, let's say, 5, the maximum number is 5, and you know those 5 different relatively prime numbers, can you make any number out of those different relatively prime numbers?
Yeah, you can represent any number that's represented in modulus M
Okay.
into modulus M1, modulus M2, modulus M3, modulus M4. Yeah.
I think maybe I can put it better. Is there a unique?
I was not talking about uniqueness, but to answer your question, yes, it's a unique and it's bijective. So if you go from the broken space into the original, it goes back into one number. And if you go from the number to the representation, it goes to one set of components. So it's bijective representation. Otherwise, it's not going to be very useful when you do operations, right? Because you lose information in one direction.
Yeah.
Okay. Any other questions?
But I thought it's like the resultant vector and its components. Like
Similar, very similar concept.
maybe 2 components can be the same, but not all 3 of the.
No. Any vector and another vector, they will not have the same components unless they are exactly the same vector. Otherwise, it's different, right? So same here. Unless x and y are equal to each other, you will not have the same representation of x and y in the subspaces, right? Or in the sub-modulus. Okay?
But their A's and B's can be the same without their C method.
خلاص ما هو at least one component. مفيش very similar. At least one component is different. Unless they are exactly the same thing. تمام?
Regarding theorems, looking at which one would be our main focus? Because that's kind of similar.
No, they are not kind of similar. We did not start using them yet. We just mentioned a set of theorems. Later on, we will see which one of those. All of them are going to be used to explain something that happens in encryption, but we will see how this helps us to understand this part of encryption, how that helps us understand that part of encryption. Come on, we took only 3 theorems so far. The other stuff is like trivial. Don't tell me that you get confused by getting a remainder while adding 2 numbers mod n. This is يعني grade 4 or grade 5 arithmetics.
We're about adding numbers and doing all these processes, but we're not doing it. So it's so jumbled up.
Okay, we'll do examples next time, inshallah. We'll do numeric examples next time. Okay, inshallah. Okay, so here is what the Chinese remainder theorem says. And probably I've already mentioned most of it, right? If you have a modulus M which can be represented by a multiplication of submoduli mi, right? Where those mi are pairwise relatively prime, so mi and mj, they don't have a greatest common divisor except 1 for all I and j, not equal to each other, okay? Then, any integer a that belongs to the original space Zm. By the way, when we say Zm, it's the set of integers that exists in modulus m. So Zm contains what? What are the possible values?
M1, M2,
0 لحد
M minus 1.
until m minus 1. Bravo. Okay, so this is our space of Zm.
Why did we start with 0?
عشان 0 exists in modulus arithmetic, right? If I say, for example, 8 mod 8, this is equal to what? 0. 0. It's not the result of the division, it's the remainder of the division. If you divide 8 by 8, the remainder is equal to 0, right? So the remainder in modulus arithmetic talks about the remainder. A remainder can have a value from 0 up to the divisor minus 1, right? So it can have a value from 0 up to the modulus. The divisor here is our modulus. Okay. Okay. So any integer that belongs to the finite, we call this finite field. Okay. The finite field Zm can be represented by a k-tuple whose elements ai belong to these sub-finite domains, which are the domains modulus M1, M2, M3, and so on. Tamam? Using the following correspondence, A is equal to, again, just as if it's a vector representation. Tamam? That's the k-tuple that we are talking about. Okay? Where those AIs are simply A mod MI. So A1 is A mod M1, A2 is A mod M2, A3 is A mod M3, and so on. Yes.
Is it similar to the projection of vectors?
Yes, it's not projection, it's analysis of a vector into its prime components, or projection into subspaces. I have a vector in the big space M of dimension capital M, for example, and then I want to represent it as projections into smaller spaces of dimension M1, M2, M3, M4, and so on. Okay.
And Z is just all of the different projections, let's say? What is the importance of Z exactly?
ده بس defines the space. This number can have a value from 0 to m minus 1. This value, this A, is represented in the space Zm. So it cannot be, لو Zm مثلا, for example, I'm dealing with modulus 10, I cannot have an A which is equal to 100 because it can only take values from 0 to 9. Okay, so it just tells you that the value of A belongs to this modulus space. Okay.
My question last slide was not considering that assumption that A must be within Zm. So when you said it's unique, I was so confused.
Okay.
How can it be unique?
Yeah. Because it's limited to the space. Otherwise, there are many other numbers that are congruent to the same value and they go outside the range Zm. Yes. No. It's that A, or the number that we are breaking down, is mod M already.
Yeah.
Okay.
It's unique inside the modulus range? Or
Yes. Okay. And again, the theorem continues that this mapping is a bijection, so it's unique in both directions. If you see it here, it corresponds to 1 over there. And if you see it here, it belongs to 1 only over there, right? And the operation on elements of Zm can be performed by carrying them on the corresponding k-tuples independently in each coordinate. Okay? So if you do addition, you add the different elements on the same place. If you do multiplication, you multiply the different elements on the same domain, which is not quite similar to what we do in vector multiplication. Because vector multiplication has a couple of definitions, either cross or dot, and it has a totally different definition. But here, any operation that you do it only, the same operation, you do it on the elements of the same subspace. You add them, you subtract them, you multiply them. Okay? That's slightly different from the typical vector space.